Coding Essentials, the development tools hash. At a very high level, the Decentraland Software Development Kit SDK allows you to do the following. Generate a default project containing a Decentraland scene, including all the assets needed to render and run your content. Build, test, and preview the content of your scene locally in your web browser completely offline and without having to make any Ethereum transactions or own land. Write TypeScript code using the Decentraland API to add interactive and dynamic behavior to the scene. Upload the content of your scene to the content server. Link your land tokens to the URL of the content you have uploaded. Our SDK includes the following components. The Decentraland editor, an extension for Visual Studio Code that allows you to create scenes, preview and debug, and publish. Read more. The Decentraland ECS, a TypeScript package containing the library of helper methods that allows you to create interactive experiences. Use it to create and manipulate objects in the scene and also to facilitate in-world transactions between players or other applications. Latest ECS reference. The Decentraland CLI command line interface. Use it to generate new Decentraland scenes locally on your own machine. Preview them and upload them to the content server. Scene examples. Take inspiration and coding best practices from the scene examples. Requirements hash. To develop a scene locally, you don't need to own land tokens. Developing and testing a scene can be done completely offline without the need to deploy a scene to the Ethereum network the system Decentraland uses to establish ownership of land or the content server. You must have the following. Visual Studio Code. Download it here. Beyond hosting the Decentraland editor extension, it helps you create scenes a lot faster and with less errors. A source code editor marks syntax errors, autocompletes while you write, and even shows you smart suggestions that depend on the context that you're in. You can also click on an object in the code to see the full definition of its class and what attributes it supports. The Decentraland editor, an extension for Visual Studio Code that exposes many common functionalities as buttons in the UI. How to install it. Supported languages and syntax hash. TypeScript hash. Decentraland employs TypeScript, TS, as the default language for writing scenes. TypeScript is a superset of JavaScript, so if you're familiar with JavaScript you'll find it's almost the same, but TypeScript includes type declarations. Thanks to type declarations, it's possible to have features like autocomplete, better debugging hints. These speed up development times and allow for the creation of a more solid codebase. These features are all key components to a positive developer experience. When a scene is built, the TypeScript code you wrote is compiled into minified JavaScript to make it lighter. The original source code in TypeScript is never uploaded to the servers, only the compiled JavaScript version. Other languages hash. You can use another tool or language instead of TypeScript and compile it into JavaScript, as long as your compiled scripts are contained within a single JavaScript file named game.js. All provided type declarations are made in TypeScript, and other languages and transpilers are not officially supported. Scenes hash. The content you deploy to your land is called a scene. A scene is an interactive program that renders 3D content. This could be a game, an interactive experience, an art gallery, whatever you want. Scenes are deployed to virtual land in Decentraland. Land is a scarce and non-fungible asset maintained in an Ethereum smart contract. Deploy to a single parcel, a 16 meter by 16 meter plot of land, or to multiple adjacent parcels. When players visit Decentraland, they download and render the content of each scene as they walk through the map. They unload scenes as they walk away from them. You can also run a scene locally on your machine by running a preview from the CLI. You can also upload a preview to run remotely on a third-party server to easily share your work with others. Entities and components hash. Three-dimensional scenes in Decentraland are based on an entity component system architecture, where everything in a scene is an entity. Entities have components. Each component gives the entity it belongs to specific properties. A door entity is likely to have at least a transform component that sets position, rotation, and scale, and another to provide it a shape. Components are just a place to store data. They don't carry out any actions. / create an entity const equals engine. Add entity. / give the entity a position via a transform component transform. Create door, position, vector 3. Create 5, 1, 5 / give the entity a visible shape via a GLTF container component GLTF container. Create door. The default set of components are interpreted by the engine and have direct consequences on how the entity will look, its position, if it emits sounds, etc. You can also define custom components to store data that might be useful to the mechanics in your scene. The engine won't directly interpret what the values on these components mean, but you can write logic in your scene's code to monitor these values and respond to them. For example, I can define a custom door state component to track the door's open / close / lock state. In this case, the component is nothing more than a place to store a value that keeps track of this state. I have to implement the logic that interprets these values separately. Entities may be nested inside other entities to form a tree structure. If you're familiar with web development, you might find it useful to think of entities as elements in a DOM tree and of components as the attributes of each of these elements. Entities are an abstract concept. An entity is just an ID that is used as a reference to group different components. See entities and components for an in-depth look of both these concepts and how they are used by Decentraland scenes. The game loop hash. The game loop is the backbone of a Decentraland scenes code. It cycles through part of the code at a regular interval and does the following. Listen for player input. Update the scene. Re-render the scene. In most traditional software programs, all events are triggered directly by player actions. Nothing in the program state will change until the player clicks on a button, opens a menu, etc. But interactive environments and games are different from that. Not all changes to the scene are necessarily caused by a player's actions. Your scene could have animated objects that move on their own or even non-player characters that have their own AI. Some player actions might also take multiple ticks to be completed. For example, if the opening of a door needs to take a whole second, the door's rotation must be incrementally updated about 30 times as it moves. We call each iteration over the loop a tick. Decentraland scenes are rendered at 30 ticks per second whenever possible. If the machine is struggling to render each tick, it may result in less frequent updates. In each tick, the scene is updated, then the scene is re-rendered based on the updated values. In Decentraland scenes, there is no explicitly declared game loop, but rather rather the systems of the scene make up the game loop. The compiling and rendering of the scene is carried out in the backend. You don't need to handle that while developing your scene. Systems hash. Entities and components are places to store information about the objects in a scene. Systems hold functions that change the information that's stored in components over time. Systems are where we implement game logic. They carry out the actions that need to be updated or checked periodically on every tick of the game loop. A system is a pure and simple function that gets called once on every tick up to 30 times a second, following the update pattern. / basic system function my system console. Log my system is running engine. Add system my system. / system with dt function my system dt number console. Log time since last frame dt engine. Add system my system dt. A single scene can have 0 or many systems running at the same time. Systems can be turned on or off at different moments during the scene's duration. It's generally a good practice to keep independent behaviors in separate systems. See systems for more details about how systems are used in a scene. Querying components hash. You can query components with a method engine. Get entities with components. To keep track of all entities in the scene that have certain components. It often makes sense to query components within a system to then loop over each of the returned entities and perform the same set of actions on each. If you attempt to iterate over all the entities in the scene on every tick of the game loop, that could have a significant cost in performance. By referring only to the entities returned by a query, you ensure you're only dealing with those that are relevant. / define a system function box height system dt. Number / query for entities that include both mesh renderer and transform components for const entity of engine. Get entities with mesh renderer. Transform const transform equals transform. Get entity console. Log of boxes at height. Transform. Position. Y. / add the system to the engine. Add system rotation system. Mutability hash. You can choose to deal with mutable or with immutable read-only versions of the component. The get function in a component returns an immutable version of the component. You can only read its values, but can't change any of the properties on it. The get mutable function returns representation of the component that allows you to change its values. Use mutable versions only when you plan to make changes to a component. Dealing with immutable versions of components results in a huge gain in performance. Fetch an immutable version read-only const immutable transform equals transform. Get my entity / the following does not work. / immutable transform. Position. Y. equals to const mutable transform equals transform. Get mutable my entity / the following does change the entity's position mutable transform. Position. Y equals to. See mutable data for more details. Putting it all together hash. The engine is what sits in between entities and components on one hand and systems on the other. All of the values stored in the components in the scene represent the scene state at that point in time. With every tick of the game loop, the engine runs the functions of each of the systems to update the values stored in the components. After all the systems run, the components on each entity will have new values. When the engine renders the scene, it will use these new updated values and players will see the entities change to match their new states. Create an entity const cube equals engine. Add entity. / give the entity a position via a transform component transform. Create cube position. Vector 3. Create 5, 1, 5 / give the entity a visible shape via a mesh renderer component mesh renderer. Set box cube / define a system function rotation system dt. Number / query for entities that include both mesh renderer and transform components for const entity of engine. Get entities with mesh renderer. Transform. Const transform equals transform. Get mutable entity transform. Rotation equals quaternion. Multiply transform. Rotation. Quaternion from angle axis dt asterisk. 10 vector 3 up / add the system to the engine. Add system rotation system. In the example above, a cube entity and a rotation system are added to the engine. The cube entity has a transform and a mesh renderer component. In every tick of the game loop, the rotation system is called, and it changes the rotation values in the transform component of the cube entity. Note that most of the code above is executed just once when loading the scene. The exception is the rotation system, which is called on every tick of the game loop. Scene decoupling hash. Your scenes don't run in the same context as the engine aka the main thread. We created the SDK in a way that is entirely decoupled from the rendering engine. We designed it to be like this for both safety and performance reasons. Because of this decoupling, your scene's code doesn't have access to the DOM or the window object, so you can't access data like the player's browser or geographical location. The decoupling works by using RPC protocol. This protocol assigns a small part of the client to only render the scene and control events. We have also abstracted the communication protocol. This allows us to run the scenes locally in a web worker. We don't want developers to intervene with the internals of the engine or even need to know what lies inside the engine. We need to ensure a consistent experience for players throughout the Decentraland map, and mistakes are more likely to happen at that low level. This decoupling is also important to prevent neighbor scenes from interfering with the experience of players while they're on someone else's scene. A player might have multiple nearby scenes loaded at the same time, each running their own code. Some actions like opening external links or moving the player are only permitted when the player is standing on that particular scene, not if the scene is loaded but the player is outside. Tree shaking hash. When converting the source code in TypeScript to the compiled code in Minify JavaScript, the process performs tree shaking to ensure that only the parts of the code that are actually being used get converted. This helps keep the scene's final code as lightweight as possible. It's especially useful when using external libraries, since often these libraries include a lot of functionality that is not used that would otherwise bulk up the scene. As a consequence of tree shaking, any code that you want your scene to run needs to be referenced one way or another by the entry point of your code index ts. Any code that is not explicitly or indirectly referenced by this file will not make it into the scene. For example, suppose you have a file named extra content ts with the following content. The entity will not be rendered and the system will not start running. Extra content ts const my entity equals engine. Add entity. Transform. Create my entity position x8y0z8 mesh renderer. Set box my entity function. My system dt. Number console. Log system running engine. Add system my system. To make it run as part of your scene, you can reference from index ts in the following way. / on extra content ts export function add entities const my entity equals engine. Add entity. Transform. Create my entity position x8y0z8 mesh renderer. Set box my entity. Export function my system dt. Number console. Log system running / on index. ts import add entities my system from / extra content add entities engine. Add system my system. In the alpha release of sdk7, all scenes must include the following line in index ts. This imports the essential elements from the SDK which would otherwise not be imported due to tree shaking. Export asterisk from a DCL / SDK. SDK versions hash. When developing a new scene, you use that latest stable SDK release by default. You can install that next SDK release if you want to leverage or preview upcoming features that didn't yet make it into the latest stable release. To do so, open the Decentraland editor tab and press the plus sign to install the following. A DCL / SKD at next. See manage dependencies for more details. Note, keep in mind that the next version might suffer issues from time to time. The syntax and name of new features might change before it's released in a stable version.